All right, here we go. So today we are going to learn about how to use the ideas of work and energy to calculate non-conservative forces. All right. So first of all, we should talk about work, right? In the last unit, one of the things we learned was how to calculate work. And we established that work is always done by a force, right? You can find the work done by friction, which is dependent on the force of friction, or the work done by Roy, which is dependent on the force of Roy. And what we learned was the easiest way to do it, or the most common way of doing it, is to multiply your force times your displacement, right? Now, that relies on the fact that your force is parallel to your displacement. If they are not parallel, then you need to split that force up into components, and we just care about the parallel component, okay? All right, so that's how you calculate work. And so what we also learned was this idea of the law of conservation of energy. And what we learned was if no non-conservative forces do work, then your total energy is constant, right? And so we applied that a ton in these like roller coaster problems, right? So here's a simple example of one, right? So my roller coaster is going over the top of this first hill at 10 meters a second. It's 40 meters tall. The problem is telling us that the second hill is 15 meters tall. What's the velocity at the top of that hill, right? So what we would do is we'd calculate the total energy at the top of the first hill. So we'd go, oh, I know the velocity. So I can find my kinetic energy. It's 3,000 joules. Oh, I know the height, so I can find my GPE. It's 23,520 joules. That means my total energy is 26,520 joules. All right, well, what's happening as I go down the hill? What forces are there? Well, there's gravity, which is conservative, so I don't care about that. And there's normal force, which is non-conservative, but it's always perpendicular to the motion, right? And so it doesn't do work. And then there's no friction, so that's it, right? So since no non-conservative forces do work, that means our total energy is constant. So when I get to the second hill, my total energy is still going to be 26,520 joules. My GPE here, if you figure it out, turns out to be 8820 joules, which means the kinetic energy must be the difference, which is written on a piece of paper that I have over here. I guess I didn't write it down, but anyway, you can find that kinetic energy and then use it to find the velocity, and it turns out to be 24.5 meters a second, okay? But that's all review, and you've done that, right? So, but again, the reason that these two total energies here are equal is because our non-conservative forces didn't do work, all right? And so the question is, what happens if our non-conservative forces do work? And so what happens then is this. It turns out that the work done by all the non-conservative forces on an object equals the change in total energy. This guy, okay? And so this buys us a lot in terms of problem solving, all right? And there are actually 3 work energy theorems. This is one of them. These other 2, if you take AP, we'll talk about those more, okay? But I'm not going to worry about them this year. All right, so the work done by non-conservative forces are change in total energy. And so that buys us some stuff in terms of problem solving. All right, and so let's talk about work and energy and kind of how we relate these two ideas. This slide here tells us kind of all of the work energy equations that you need to be successful this unit. All right, so the first one is the one we just learned. The work of non-conservative forces is our change in total energy. Okay, oops. Now, what do I mean by work of non-conservative forces? Well, that's the work of all of the forces other than gravity and springs. So the work of non-conservative forces is, excuse me, the work of Roy plus the work of friction plus the work of the normal force. Often 0, but not always 0. Okay? All right, and then we know how to calculate work like we talked about back in that first slide, right? You can just do force times displacement. And because work is equal to a change in total energy, we should make sure you know how to deal with change in total energy. So one way to do it is anytime you do change, it's always final minus initial, okay? So that's going to be the most common way of finding our change in total energy, is to do final minus initial. Occasionally, we're going to solve problems with systems. And for those problems, it ends up actually being easier to calculate your change in total energy this way, by finding your change in kinetic energy, your change in gravitational potential energy, your change in spring elastic potential energy, if that's relevant in the problem, and adding those up, okay? So let's see if we can apply this to a problem. All right, so the first one's going to be a little bit oversimplified just because I want to make sure you kind of understand the concept, but we're going to revisit this roller coaster problem, but this time it's not going to be frictionless. All right, so I'm going to cheat. Copy. Cool. All right, so here is our roller coaster. The big difference is this time our roller coaster has friction. Okay, but what you can see is the initial conditions of my roller coaster are the same. I'm still moving at 10 meters a second and I'm 40 meters up. So if you calculate it, here's your total energy you get, 26,520 joules, right? But what you can see is now, due to the friction, the velocity at the top of the second hill isn't 24 meters a second, it's only 20 meters a second, right? The friction slowed us down, okay? So let's do the same thing. Let's figure out what our total energy is, okay? So if you find your kinetic energy here, you get 12,000 joules. And if you find your GPE, you get that same 8,820 joules, which means my total energy now is only 20,820 joules, right? I lost some energy, didn't I? My total energy went from 26,000 down to just 20,000. Well, that change in total energy is a result of the work done by non-conservative forces. So what are the non-conservative forces? Well, as you're going down the hill, you're going to have gravity. That's conservative. We don't care about it. Normal force is non-conservative, but it doesn't do work because it's perpendicular to the motion. And we've got friction, right? The friction, if you're going down the hill, then the friction is going to be up the hill, right? Like this, right? So that frictional force is always parallel to my displacement, so it's doing work, all right? So for this problem, here's what's going to happen. Check it out. We've got work of friction is the work of non-conservative forces. That's equal to my change in total energy. So that's TE final minus TE initial. So that's 20,820 joules minus 26,520 joules. And so you get negative 5,700 joules. And that's the work done by friction. So now what I can do is this. Work of friction is force of friction times displacement. They're already parallel. Negative 5,700 joules equals the force of friction times 100 meters, because that's how far the train moved between those two hills. And so divide, and your force of friction is negative 57 newtons, which isn't a very big frictional force, which is what you would hope for on a roller coaster, right? Because you don't want to lose energy on the roller coaster, right? It is worth noting, though, on this one, because the track is curved, that means your normal force is always changing, which means your friction force is always changing. So this is actually just an average force of friction, all right? So usually we only use work equals force times displacement if your force is constant, okay? And honestly, I think other than this one example, our force always will be constant, okay? When we deal with springs, we have to work around another way of doing it because spring forces are not constant. Okay, so that's kind of the gist of this, right? So what we're going to do is we're going to use our change in total energy to find the work of non-conservative forces, and then we do work equals force times distance to find a missing force or sometimes a missing distance, all right? So let's do another example that's maybe more similar to what you might see on a homework assignment. So here what we're going to have is just a straight ramp, okay? And so our normal force isn't changing. The other difference here is we've got two non-conservative forces. All right, so here we go. We got a 12 kilogram box sliding from rest down a ramp that's 5 meters long and 3 meters tall. So let's make a little drawing. So here's my ramp. The problem tells me it's 5 meters long. So that's going to be my displacement as the box slides down the ramp. Here's the box. I know that at the top of the ramp, the height is going to be 3 meters, and it's sliding from rest. Okay, as it slides down the hill, it says we're going to have 25 newtons of friction. So let's go ahead and put that on our drawing. Force of friction is 25 newtons. Use work and energy to find the force Roy needs to apply if he doesn't want the velocity at the bottom to exceed 4 meters a second. So that means by the time we get to the bottom, our velocity can be at most 4 meters a second. Okay? So we're going to kind of do the same thing. We're going to find the total energy at the top and the total energy at the bottom. So if you do this, this GPE here turns out to be 352.8 joules. The kinetic energy at the beginning is 0. That means the total energy initially is 352.8 joules. Now, when you get down to the bottom, now the GPE is 0, but we've got some KE totaling 96 joules. And here I'm just doing MGH and 1/2 mv squared. I'm not writing all that out because you hopefully know how to do that by now. All right, so this total energy is only 96 joules. I lost some energy. So let's calculate the work done by non-conservative forces. Well, that's TE final minus TE initial. So 96 minus 352.8. And so you get negative 256.8 joules. So that's the work done by non-conservative forces. Well, but what is that, though? What do I mean when I say the work done by non-conservative forces? Well, in this problem, there are two non-conservative forces. Oops. So the work of non-conservative forces here is work of friction plus the work of Roy. Oh, well, we can find the work of friction because we know the force of friction, right? So the work of friction is force of friction times displacement. I got 25 newtons of friction and 5 meters of displacement, so that's 125 joules. Please note it's negative because my displacement is down the ramp and my friction is up the ramp. Remember, anytime your force opposes your motion, negative work. Cool? So now I can figure out how much work Roy does. The work of non-conservative forces is negative 256.8. That's equal to the work of friction plus the work of Roy. So now I can add 125 to both sides to find out that the work of Roy is negative 131.8 joules, right? So friction took away some of the energy. Roy has to take away the rest of the energy to make sure we lose that 256 that we were trying to lose, right? And so now I do work equals force times distance. Work of Roy is force of Roy times displacement. Displacement is 5 meters because that's how long the ramp is. And the force of Roy turns out to be 26.4 newtons up the ramp. Okay, so that's a little more like what you'll see on the homework assignments, okay? All right, finally, one last example. We need to talk about what happens if there's a pulley in your problem, okay? And this complicates things just a little bit, all right? So here what we've got is we've got this box. Box A has a mass of 12 kilograms. Box B has 1.2 kilograms. Box B has a mass of 0.4 kilograms. The system is released from rest. And the question wants to know what's the final velocity going to be after box B falls 0.5. No, I lied. We're not looking for the final velocity. I apologize. Boop, 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 boop. It tells us that box B is going to fall 0.5 meters. So my change in height for box B is negative 0.5 meters, right? Because it's going down 0.5 meters. And then it tells us that at the end of that time, our final velocity is now 0.8 meters per second. But notice that's got to be the velocity of both boxes because they're tied together. Okay? And so what we're trying to do is we're trying to find the force of friction on box A. Oh, I wanted that to be red. Well, I guess I can just do it again. Oh my goodness, there we go, force of friction. So that's what we're trying to find. All right, so here is what we are going to do. I'm going to take advantage of the fact that friction is my only non-conservative force here. So the work of friction is the work of non-conservative forces, and that's my change in total energy. And my change in total energy is my change in kinetic energy plus my change in GPE. Now notice, my starting kinetic energy is 0. So technically speaking, change in kinetic energy is KE final minus KE initial, right? So what I'd have to do is find my final kinetic energy, my initial kinetic energy, and subtract. But here, my initial kinetic energy is 0, so I don't even care about that. Okay? So it's really just my final kinetic energy. So what is that final kinetic energy? Well, it's 1/2 mv squared. So 1/2 times, what's my mass? Well, I have a total of 1.2 plus 0.4, so that's 1.6 kilograms in motion. And they're both, that all of that mass is moving at 0.8 meters per second. Okay, so that's my change in KE. Clean up my board here a little bit. All right, plus my change in GPE. So remember, change in GPE, there's a shortcut, right? We can do mg delta H, and just be careful. Moving up is positive delta H, moving down is negative delta H. So here, now the question though is what mass is losing GPE, and it's just box B. So this mass is different than the mass that you use for the kinetic energy, okay? So, board's getting cluttered. I did a rotten job managing my board space here. So we're gonna do times the mass, 0.4, times 9.8, times my change in height, which is negative 0.5 meters. Make a note, this is total mass, this is just mass B, okay? All right, and so let's figure out what this value is, because that's going to tell me the work of non-conservative forces, because it's how much my total energy changed. So if you do this, you get, why can't I find my papers? Let's see, you get 0.512 joules of kinetic energy minus 1.96 joules of GPE for a total loss of 1.448 joules of energy, and that's equal to the work done by friction. And so now I can find the force of friction, right? Because work of friction is force of friction times displacement. So I lost 1.448 joules of energy. That's equal to the force of friction times how far did box A move? Well, if box B went down 0.5 meters, then it pulled box A forwards 0.5 meters. So there's my displacement. So divide, and your force of friction ends up being negative 2.896 newtons worth of frictional force. All right, there we go. That's how you calculate that's how you calculate non-conservative forces.